All right, Calc, this is section 2.4, dealing with complex numbers. There's a bunch of problems on the back side of this note sheet. There's quite a few of them, but they generally go by pretty fast, or they're not a whole lot of work. So I'm going to try to go through this pretty quick. The two things that you need to remember for complex numbers is that get a different pen that actually works. I is the square root of -1. The reason why we have to have imaginary numbers exist is because we can't take the square root of a negative. So they've defined I to be the square root of -1, so that way we can reduce any number, even if it has a negative inside a square root, to an imaginary number. Given that, if we square both sides, I squared would then be the square root of -1 squared, which the square root and the square would drop off, so I squared is -1. So those two things, remember those, and that will help you simplify things as we go through here. Okay, so definition of complex number. Complex numbers are usually written in the form of a plus bi, where a is like just a regular old number, and then b is the part that's attached to the imaginary number. This might be like 3 plus 2i, or 7 minus 4i, okay? You'll notice that these, when they're written in standard form, kind of resemble like the quadratic formula. So we'll deal with plus and minus, like 3 plus and minus 2i, 7 plus and minus 4i, that type of thing. So let's see. A plus bi is called an imaginary number. I'm trying to think. Oh, if it does not have the a part, like a is 0, and it just has bi, so if it just has like 4i, or 2i, or -7i, those are called pure imaginary numbers. Okay, so they might use that notation in the book. I don't use that a whole lot, but there's how that works. All right, so where do complex numbers or imaginary numbers fit in like the scheme of all the numbers? So real numbers are every single number that exists. So if you're looking at like a Venn diagram that has all of the real numbers, we have real numbers. It's every number that you can think of. And then we have, within that, we have rational numbers, and we have irrational numbers. Okay? Rational numbers. If this is the bubble of rational numbers, then within those we have integers. Then within those we have whole numbers. And within those, we have natural numbers. Okay, so rational numbers, integers, whole numbers, natural numbers. Integers are negatives and positives. Whole numbers are just positive numbers, including 0. Natural numbers are just the numbers like 1, 2, 3, 4, 5, 6, blah, blah, blah. Rational numbers, though, will also include decimals. Irrational numbers are kind of like decimals, but these guys don't repeat. So this would be like the square root of 2. That can be made into a decimal, but that decimal never repeats, never stops. So that's what makes them an irrational number. Same thing with pi, etc. Right? Those are all our real numbers. All right. Now, where do complex numbers fit, or imaginary numbers? They fit over here. This is where the imaginary numbers live. So any number that you can think of doesn't include imaginary numbers, because those are like fake numbers. So these are real numbers, and these are like fake numbers, which kind of is a good way to think of them. Real numbers, fake numbers. So imaginary numbers do not live inside of the real numbers. Now, you can have real numbers be a part of the imaginary numbers, like in the a plus bi, right? This guy is going to be a real number, but since he is attached to an I, it makes him an overall imaginary number. All right, so he will have a part that's real, but overall he will be an imaginary number. All right, so let's get down to this. Equality of complex numbers. So if a plus bi equals c plus di, then a has to equal c and b has to equal d. Those things have to be true. So operations in complex numbers. This is just like treating I as an x. So you can add i's to other i's. You can only add them and subtract them if they have the same unit behind it. So I could not, for example, add a and d together, right? Because one has an I, one doesn't. I can only add b and d and a and c. Those guys are the only pairs that I'm able to put together. So a plus c, b plus d, and then there's an I attached to that. Same thing with the difference if I'm subtracting. The one thing there is to make sure to distribute the negative. Distribute negative. This guy has to go there and there. Okay, so let's go do some of this stuff on the back side. I'm going to skip this top part. The additive identity is 0. Anything you add to 0 stays the same. etc., right? Adding and subtracting. So, since I'm adding, I'm just going to take and add the parts that I can together. So 3 plus 2 is 5. Negative I plus 3I is plus 2I. And that is all I can do. Okay? All right. So number 2 has a little bit more involved in there. And I'm going to go ahead and get rid of my parentheses. So this is 3 minus a negative 2 plus 3I. So I'm going to take that negative and I'm going to distribute them through. So the 3 is going to stay. Minus a negative 2 is going to become plus 2. Minus 3I. And then I have plus a negative 5. So I'm going to do minus 5. And plus a positive I. So plus I. And then I just combine things that I can. So 3 plus 2 is 5. Minus 5 all goes away. So there's that. Okay, and then negative 3I plus I is negative 2I. And this is that pure imaginary number, like we saw from the front side. If it doesn't have an A part of it, if it just has the BI part, that's called a pure imaginary number. Okay? All right, so that's addition, subtraction. Make sure that you're being careful when you are distributing negatives. That's about all I can say for that. Multiplying, this one is just distribute. So 4 times negative 2, negative 8. Plus 12I, can't do anything else, that's all. All right, number 2, if I take I and negative 3I, that's negative 3I squared. Now, if you have something bigger than I, like I squared or I to the third or I to the fourth, etc., you have to reduce it. So I know from the front side, I'll use a different color even, I know from the front side that I squared is equivalent to negative 1. And that negative 1 and that negative 3, you don't add them together. You multiply them, because negative 3 is multiplied by I squared, so negative 3 is multiplied by negative 1, and that will become positive 3, and that is my final answer. So if it is bigger than I, like I squared, I to the third, etc., you are going to want to reduce that. Okay? All right, now 3. You cannot just distribute the negative, right? This isn't just like 9 plus 4I squared or anything like that. You have to FOIL. So this means that we're doing it twice. We are multiplying twice. Okay? 3 times 3 is 9. 3 times 2I is 6I. 2I times 3 is another 6I. Some of you guys can skip this middle step and add those together at the same time. That's fine. Go ahead and do that. And then 2I and 2I makes 4I squared. Okay? Now, if I put these middle two pieces together, that's 12I. But we always reduce if it's bigger than I squared is negative 1. So positive 4 times negative 1 will make this negative 4. Okay, so now when I put my pieces together, I've got 9, I've got 12I, and I've got negative 4. 9 and negative 4 can go together, that makes 5, plus 12I, and there he is. Okay? All right, now, almost the last thing, okay? We have something called complex conjugates, okay? And what that does, complex conjugates, when you're dealing with the conjugate of a complex number, like let's say I start with 3 plus 2I. 3 plus 2I, the conjugate of that guy would be 3 minus 2I. Because most of the time, or really the reason why i's exist is for quadratic functions when we're taking the square root. Like if I were to solve x squared equals negative 4, right? I would take the square root, and that would give me x equals, the square root of 4 is 2, but the square root of the negative would make I. So 2I. But not only is x equal to 2I, but it's plus and minus because we inserted the square root in there. So anytime you see a complex number, his conjugate pair will always go with him. It's kind of like in the quadratic formula where you always have plus and minus, okay? So you'll always see that quadratic, or that pair that goes with him, okay? When people get confused, they might see like negative 4 plus 3I, right? They want to do positive 4 plus 3I. It's only the I part that changes, right? So this stays negative 4 minus 3I, right? The front part does not change. It's only the part that's attached to I, okay? And they really might try to confuse you by saying, like, let's say 5I plus 6. Well, it's not 5I minus 6. It's negative 5I plus 6 because it's the I that's going to be changed, all right? So they want us to multiply each number by its complex conjugate. So 1 plus I, the conjugate of that is going to be 1 minus I. We change the sign in front of the I, all right? So 1 times 1 is 1. 1 times negative I is negative I. I times 1 is positive I. and then I times negative I is negative I squared. Okay, negative I squared. So now I put my pieces together. Negative I positive I goes away, and then I squared is the same thing as negative 1, right? So we have a negative, negative 1, right? Minus I squared was minus a negative 1. So we have 1 plus 1, which is 2, okay? You will notice that when you multiply a number by its complex conjugate, a complex number by its conjugate, the i's will always go away, and that's done on purpose, okay? 4 minus 3i, if we multiply him by his conjugate, he will be 4 plus 3i. So 4 times 4 is 16, 4 times 3i is plus 12i, and then there's that middle piece that's going to cross out again. Negative 3i plus, or times 4 is negative 12i. That's going to cancel out. And then negative 3i times positive 3i is going to be negative 9, but then we have I squared. Okay? All right, now again, that I squared is going to become negative 1. So we've got negative 9 times negative 1, which is positive 9. All right, now we have 16 times positive 9, or plus 9, excuse me. 16 plus 9, so that gives us 25. Okay? It will always be the case that a complex conjugate, when they are multiplied together, the i's will always go away. All right, now, the reason why they had us do that in those two steps was just like having a square root in the bottom of a fraction, like we learned in chapter 9 in trig functions, right? Like this 1 over the square root of 2 should be like the square root of 2 over 2, right? We like to multiply by square root of 2 over square root of 2, okay, to get square root of 2 over 2. It is improper to have an I in the bottom. We can have an I on the top, but we can't have an I in the bottom. So what we do to get him out of there is we multiply him by his complex conjugate. So 2 plus 3i over 4 minus 2i. The thing that I have a problem with is the 4 minus 2i. So I'm going to multiply by 4 plus 2i. And if I do that to the bottom, I have to also do it to the top. Okay, so complex conjugate 4 minus 2i, I'm going to do 4 plus 2i, because then I'm not going to end up with an I in the bottom anymore. All right, so I've got that. So 2, if we FOIL, 2 times 4 is 8. 2 times 2i is 4i. I'm kind of going through this stuff really fast. So if I'm going too fast, make sure you pause the video or whatever and slow me down. 3i times 4 is 12i. 3i times 2i is 6i squared. Okay, and then we're going to simplify him, but we'll just wait a second. 4 times 4, let's do the bottom. 4 times 4 is 16. 4 times 2i is 8i. Negative 2i times 4 is negative 8i. And then negative 2i times 2i is negative 4. But then we have an I squared. Okay, so the bottom, on the bottom, 8i and negative 8i are going to cancel out. They didn't do that on the top, but that's because I wasn't multiplying by the conjugate on the top, right? Just the conjugate on the bottom, okay? So up on the top, I have an I squared that can change to negative 1, and on the bottom I have an I squared that can change to be negative 1. Okay, so if I multiply by 6 on the top, 6 times negative 1, that whole thing will become minus 6. The whole thing on the bottom, negative 4 times negative 1, that whole thing is going to become positive 4, okay? And then let's simplify. So on the top, I've got 8 and negative 6 I can put together, which will become 2. And 4i and 12i will become 16i. That's all that's left on the top. And then on the bottom, I have 16 and 4. 16 plus 4 is 20. Okay? Now, very, very last thing. He looks like he's done because there's no I in the bottom, but if you'll notice, each one of these three numbers is divisible by 2. Okay? And you have to be able to divide all three pieces by 2, otherwise it doesn't work, or divide by any of the numbers, right? So 2, 16, and 20 becomes 1, 8, and 10. And this is your final answer. Okay? So that one was a little bit more of a process, but the more you do these, the faster you get. Okay? So there's that. All right. If you need more time on that one, pause it, go back, whatever. I'm going to keep moving. Write each complex number in standard form. Okay, so the square root of negative 3 and the square root of negative 12. Okay, the square root of negative 3. I'm going to write it in a way that might make more sense to you. The square root of negative 3 is kind of like the square root of negative 1 times the square root of 3. Right? Those two pieces, when multiplied together, will give you the square root of negative 3. Okay? But the square root of negative 1 is I. So this part right here is like the square root of 3 with an I attached. Okay? And when the I comes out, he's no longer underneath of the square root. So it's only the 3 that's under there. The I is now on the outside. Okay, now the same thing happens to 12. The square root of 12, the I will pop out, right? Because if you write this as the square root of negative 12, he would be the square root of negative 1 and the square root of 12. So this would be I times the square root of 12 or square root of 12I. Okay, so we do that. And there we have that. And then we can just multiply the numbers together. So the square root of 3 and the square root of 12 will become the square root of 36. And then we'll have I squared. Okay, square root of 36, I squared. Well, okay, now the square root of 36 comes out nicely. It is 6. But then I squared is like negative 1, right? So we have 6 times negative 1, and it's negative 6. Okay, now, you might be wondering, do we need to include plus and minus? Because it was a square root, right? The square root of 36 is 6 and negative 6. But that square root was already there in the original problem. We did not insert the square root, right? So we are automatically assuming it was a positive 6 to start with, and then we're multiplying by a negative 1 to make it negative 6. Okay? All right, next. Let's do this. Now we are subtracting. We are not multiplying. These two are right together. That means multiply. This guy means we are subtracting. We can only subtract when they are the same, like, terms, right? Like you can't subtract x's from x squareds and that type of thing. So this guy inside of here has to be the same thing as that guy inside of there, okay? So we've got the square root of negative 48, which is the square root of negative 1, or I, times the square root of 48. But the square root of 48 can break down. The square root of 48 can break down into a couple pieces. So, oh, I don't want a circle there. I don't want a circle there. Whatever. Anyway, so I'm thinking of numbers that go into 48. Okay, I know that 4 goes in there, and 4 you can take a perfect square root of, but I want to think as high as possible. Otherwise, I'm going to have to break down multiple times. So the square root of 48 can be broken down as 16 and 3. So if I take the square root of 16 and the square root of 3, he will be 4 times the square root of 3. Because the square root of 16 is 4, the square root of 3 is square root of 3. And then where does the I fit? I usually put the I right here. 4I times the square root of 3. Whatever. It doesn't matter where you put it. But you can put the I there, all right? So I've got 4I times the square root of 3. Some people put 4 square root of 3I. We could do that too, I guess. It kind of looks, maybe it looks better that way. I don't know, we'll do it that way. 4 square root of 3I, all right? And then we have minus. Now we've got to deal with this 27, okay? So, kind of like this 48, the square root of 27 is I times the square root of 27, or the square root of 27I, right? But then 27 will break down into 9 and 3. So the square root of 9 is 3, square root of 3, and then that I comes down also. So we have 3 square roots of 3I. All right, so negative 48 is 4 square roots of 3I. Negative 27 is 3 square roots of 3I. So we have 4 square roots of 3I minus 3 square roots of 3I, which is 1 square root of 3I. And there he is. Okay, next. We're getting so close. Number 3. These problems really do go fast, but there's like 20 of them on here, so this is crazy. All right, so when we're squaring, this means negative 1 plus, and I'm going to write this not as the square root of negative 3, I'm going to write him as the square root of 3I, okay? And then negative 1 plus the square root of 3I, okay? All right, so this works just like normal. This is not a fancy problem. This is the same as what it always is. Negative 1 times negative 1 is 1. Negative 1 times the square root of 3I is negative square root of 3I. Positive square root of 3I times negative 1 is another negative square root of 3I. And the square root of 3I and the square root of 3I, okay, if we just look at the individual parts, the square root of 3 times the square root of 3 is just 3. And I times I is I squared. Okay? All right, so if you need to go back through that slower, you sure can. I squared, remember, is negative 1. Okay, so really, positive 3 times negative 1, this really is negative 3. Okay, So if I start combining my like terms, I've got 4 pieces, 1, 2, 3, 4. The 1 and the negative 3 can go together, so that's negative 2. And then I have negative square root of 3i and negative square root of 3i. Okay, if that helps you think of it as like 1 and 1, I have negative 1 square root of 3i and negative 1 square root of 3i. That would give me negative 2 square roots of 3i. Okay, and I cannot put that together anymore, so that is all. All right, so these last two examples are like really the reason why imaginary numbers exist. Okay, imaginary numbers exist when we're solving quadratic equations. Okay, a solution to a quadratic equation is where the parabola crosses the x-axis. That's it. That's all we're solving for. Except sometimes you'll have the scenario of where you have a parabola that does not cross the x-axis. And for that reason is why imaginary numbers exist, okay? Like in this guy. You'll notice that x squared plus 4, if you remember from your transformations, that's a parabola that's up 4. So he is up here at 4, okay? But when we're solving for him, what are his zeros? Where is he crossing? Well, he's not crossing anywhere, but we have to have an answer for that, right? So if we solve for x, we get x squared by itself. So x squared is equal to negative 4. And then we take the square root. So x is going to be equal to, okay, this guy is like the square root of 4 times I, right? Or 2i, because the square root of 4 is 2. And since we inserted the square root in there, we have positive, negative, okay? So this guy is crossing at an imaginary positive 2 and negative 2, right? Which really means that he's not crossing because it's imaginary, right? Now, number 2, if I look at this guy, he kind of looks like a complex trinomial, and I was thinking about this before. 3 and 5, if I multiply those together, I make 15, right? I'm looking for numbers I can multiply to get 15, but when I add them, give me negative 2. So I'm thinking like, okay, negative 5 and positive 3, right? Because those two will add together to make a negative 2, except the problem is negative 5 times 3 is a negative 15, not a positive 15. So I'm kind of stuck there. Okay, so instead of doing the complex trinomial method, let's try the quadratic formula. So we have negative b. Okay, so negative b, if b is already negative, that's a positive 2. Positive 2 plus and minus the square root of b squared, negative 2 squared is 4, minus 4 times a times c, all over 2 times a. Okay, and we'll see how this works out. So we've got 2 plus and minus 4 times 3 times 5. I'm just going to look at 4 times 5. 4 times 5 is 20, but if I take that times 3, that's 60. So I've got 4 minus 60 in here, which is a negative 56. The square root of negative 56 all over 6. Okay, so that's what I have now, and you can see how this results in an imaginary number because there's a negative inside the square root. Okay, so I'm going to take 56 and I'm going to break him down because we know he's going to be an I. 56. What was under 56 that I can take the square root of? 4 for sure. I think 4 and 14 maybe is all. 4 goes in there. 1, yeah, 4 and 14 I think is all I can do. Because 14 then won't break down anymore. So this guy, and he will have an I at the end of him. So if I do the square root of 4, that's going to be 2. And the square root of 14, and I'm going to put an I after him. Okay. Then I've got 2 plus and minus in the front and 6 behind him. Okay. And then there's one more thing that can happen. And you're like, seriously, can we be done yet? The 2 and the 2 and the 6 can all reduce. Okay. So that would be 1 plus and minus. Really, you don't have to put the 1 there, but if it helps you sleep at night, you sure can. The square root of 14i all over 3. And that is the final answer. Okay. So you'll notice this guy is a quadratic formula or a parabola. He is going to have imaginary zeros as well. So he is going to kind of resemble this guy where he's not going to touch. And we have to have imaginary answers for that. And so that is the solution. Those are the places he crosses, which means he does not cross. Okay. All right. That was much longer than I'm sure you probably wanted it to be, but there was a lot of examples on there and I kind of flew. So hopefully you got all of that. If you need to rewind, go for it.